let's derive the torsion ODE for I-beams that are not free to warp. So consider this I-beam that's restrained at one end and it's subjected to a torque. So this I-beam is going to twist, which is shown schematically here, and it's also going to warp. And the top flange is going to warp out of the plane on this side and into the plane on the other side. And similarly, the bottom flange is going to warp out of the plane on this side and into the plane on this side. Well, we can see a plan view here. So remember that our warping rotation was clockwise on the top of the flange, so it was minus the rate of twist by the height of the web on 2. And similarly over here, you had an anti-clockwise warping rotation. So anti-clockwise being positive. So this was for the condition of free warping, but where the beam is not free to warp, so in this case it's restrained at one end. So in this case, we have the warping rotation being dependent on the rate of twist, but the rate of twist is not constant along the length of the beam. And we're going to see that warping is resisted by the bending of the flanges. So recall the moment curvature equation for the bending of a beam about its major axes and the bending of the beam about the minor axes. So as we can see, the warping of the beam is going to be resisted by the bending of the flanges in the case where the beam is not free to warp. So therefore the bending moment in one of the flanges is equal to the Young's modulus by the second moment of area about the minor axes of one of the flanges, and that's multiplied by the curvature. So in this case, we have the curvature being a second order derivative with respect to z, being the direction of the axis of the beam. And as we can see, when the beam twists, we have a relationship between a lateral displacement u being equal to the angle of twist by h on 2. And this displacement in the top flange is in a negative x direction. So therefore, if we differentiate this twice and substitute for this derivative in the moment curvature relation of the top flange, we have the bending moment in the top flange is equal to the Young's modulus by the second moment of area about the minor axis of the flange. And here we have a negative sign, and h on 2 is constant. And the second derivative of the angle of twist with respect to z, being the direction of the longitudinal axes of the beam. So again, warping is resisted by the bending of each flange. So the flange is going to develop a bending moment about its minor axes. So this bending moment is accompanied by a shear force along the x direction. So differentiating the bending moment gives us the shear force in the flange. So that will be minus the bending stiffness along the minor axes by h on 2 by the third derivative of phi with respect to z. Now as we can see here, the shear forces in the flanges generate a couple to resist this torsional moment. So we'll call this the warping component, and that's equal to the shear force by the moment arm h. So what we get is the following expression. So we have h squared on 2 by the third derivative of the angle of twist with respect to z. And what we can do is conveniently multiply the second moment of area about the minor axes for the top flange by 2, and then divide this equation by 2, which gives 4 in the denominator. So therefore we can now write the warping component as minus E, or the second moment of area about the minor axes of the entire section. So noting the contribution of the web is negligible in resisting the warping, so we have h squared on 4 by the third derivative of phi with respect to z. So this torque is equal to the sum of a torsional component and a warping component. So effectively the torsional stiffness of the beam is going to resist that torque along with the bending of the flanges. And we've previously derived the torsion component from our torsional analysis of a rectangular bar. So that was the torsional stiffness, or the torsion modulus, by the first derivative of the angle of twist, being the rate of twist. And then plus the warping component, which is minus EIY by h squared on 4 by the third derivative of the angle of twist with respect to z. So previously we've derived the torsion constant for a rectangular section, which was 1/3 by the width by the height cubed. Well, for an I-beam, we sum the components of the web and the flanges. So what we have is the height of the web multiplied by the width of the web cubed plus 2 multiplied by the width of the flange by the height of the flange cubed. And this term here can be written as the warping constant, which depends on the second moment of area about the minor axes, as we saw. So our final differential equation can be written as follows. And we're going to use this equation when we analyze the buckling of an I-beam.